Tuples, dictionaries, and sets. You've already used tuples, but you probably, I wouldn't be surprised if you didn't notice. The tuples were, does anyone know where we used them before? It was in assignment 1.
First assignment.
Sorry?
The first assignment?
Yeah, but where?
Latitude, longitude pairs?
Exactly, yeah. We stored the latitude and longitude pairs of each Starbucks location in a tuple. Not a list, a tuple. So we had a list of tuples of latitude longitude pairs. I mean, really it was a list of references to tuples of latitude longitude pairs, but so we used tuples before, and tuples are similar to lists, right? There's no limit really on the data we're storing here. That's a tuple. And the big difference you're going to notice immediately is, well, we don't use square brackets, we're using the parentheses, right? That's what we're using instead, and that's how we define a tuple. And we can check, just, type, oops. It's a tuple. So there we go. We can index them like a list, get the tuple at index 2, but unlike a list, I can't do assignment. Tuples are, and what's the word I use for this? Pardon? Immutable. We can't modify them, but that's often a really good thing. You've got the data there, you leave it alone. If you really want to change it, you can't. If you really, really, really want to change it, you still can't. But you can make a copy of it and change the copy when you're creating it, fine. But you can't go in and change a tuple once it exists. And there's some, great properties about tuples. If I have some list equals basically the same thing, I say sum list dot, I get a pop-up of this. So these are all the methods, right? All the methods associated with lists. There's a few of them there. If I were to say sum tuple, on the other hand, there's really not very many. Here, I'll zoom in a little. There's only, it looks like 2 methods available. That's fine. In programming, there's always going to be trade-offs. Tuples are, there's a lot of benefits that come with tuples that you don't get with lists, and vice versa. There's always a trade-off, right? Tuples might be faster, but you can't do as much with a tuple than you can with a list, which might be slower, but you can do more with it. So there's always a trade-off there. You've actually been using tuples before, whether you like it or not. First, let me show you something like this. If I have A equals the tuple, 1, 2, no, let's do like A, B, all right, that's what we get. But what's neat is you can actually unpack the tuple. Like that. It's called unpacking. Now this is a Python thing. You're not going to see this in a lot of programming languages, but I'm showing you because it's kind of neat. And oops, what's wrong here? enumerate. In fact, look, I tried to do this as if I had enumerate, and you'll notice it says can't unpack iterable int object, which is interesting. But I'm going to go back to this, and then we see, oops, let's get rid of this. I'm doing the enumerate. But actually what you're doing here is you're unpacking the tuple. I can do this by when you do enumerate, each time through the list, it actually gives you back a tuple that we just automatically unpacked in the for loop statement. But if I didn't unpack it and just tried to store what enumerate gave me into a single variable, we actually just get the tuple, which is pretty neat. Tuples are also pretty handy because, let me show you. You can actually, now I'm going to say something that's entirely not correct. I'm going to talk about this a little bit more in a moment. But you can actually have your function return multiple values. But you're not actually returning multiple values. It's not possible to have a function return multiple values. That's not how functions work. But what it does is it returns a single tuple that has the values, the multiple values within it. You could have done the same thing with a list. You could have wrapped those things into a list, whatever. But with this syntax here, it's as if, I didn't have to type it explicitly, Python knew. It's as if I did that. I wrapped the return in the tuple. So I return a single value. It's just that that single value contains multiple values within it. And if you want to confirm that it is, return, what's the type of what it gets returned? Well, it's a tuple. If you have a function like this, you can do the unpacking though. What did I do wrong? All right, you can unpack it just like that. Now, a fun little anecdote aside, there are a lot of people, there's actually very few people these days that will say Python is a terrible language to use to teach people programming. And no one really thinks that anymore. You have to go looking really hard for those crazy people. And one of the things they'll say is, well, Python's bad because it lets people do bad things. Like it lets you have a function that returns multiple values, and that's bad. But you can't do that. Your functions are only ever allowed to return one value. But you could just wrap it in a tuple. And the joke of all that is, those people that are saying, they're like, no, C++ is better to teach, or Java is better to teach intro, because you can't return multiple values. Well, neither can you in Python. In Python, you can't return multiple values. You can wrap them in a tuple and return a single value. And you might think to yourself, well, that's just kind of like an extra step, but it's still returning multiple values. And okay, that's an interesting point. But you can do that exact same thing in all those other programming languages. You can wrap anything you want in something like a tuple and return as many values you want in Java or C or whatever. A lot of people that complain about Python don't actually know shit about Python. And so they'll make statements like, well, Python's bad because there's no such thing as pointers or something. Which is entirely false because everything in Python's a pointer. It hides it a little bit from you. They'll say things like you can't it lets you return multiple values, which is entirely not true. They'll say, well, it's not typed. Well, no, it absolutely is typed. It's just it's not strongly typed, which there is a nuanced difference. But people will often, I don't know if you've heard this, and sometimes students will think, like, oh, we're learning Python. Oh, we're learning the code in Python. Python's this fun, nice little cute world of we get to learn to code. It's too bad we're not learning like a real programming language. Python absolutely is a real deal, big kids club programming language. Let's look at the rank. Oh, look at that. The #1 programming language this year is still Python. So if you're ever thinking like, oh, we're learning Python, but it's intro and it's like a language for learning. No, it's not. It is like the most popular language. #1 is Python, and then we're looking at C, C++, Java, C#, JavaScript. This top 6 here, by the way, their syntax is all like very, 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 very similar. What's up?
Can you give an example of something that was coded with Python?
YouTube used to be originally all done in Python. Yeah. Any like data analytics stuff these days is likely to be Python. Most of the like research, any of like the big heavy duty like deep learning stuff, all like the heavy duty AI that's happening today is all like interfaced with through Python. Yeah, it's everywhere. You're gonna see things like C++ are older languages, so you see in a lot of like legacy systems that just have to, like a bank built software in the 80s and they can't get rid of it, they need it. So they'll hire programmers to maintain that legacy code. C++, I mean anything you do in one of these languages you can do in another one, it's fine. They all have little pros and cons, they're designed for certain things over the other, but they're really not. It's not impossible to do something in one language than in another. It's all the same. The C++, you're looking at like Unreal Engine, like heavy duty, like we're like heavy duty crazy optimized. You'll see like C++, C#, that's Unity. Unity is, I'm pretty sure it's all based Unity. C# is a big like enterprise software. So a lot of businesses that have in-house software, it's written in like C#, let's say. Same with like Python and all these other ones, but C#, that's kind of what it was like designed for. And you gotta know, a lot of these languages here are all pretty old. I think of these top ones here, I'm actually not sure when JavaScript popped up. '95. So these languages, the oldest one is C, then C++. So C is old. What year? '78. Right? So C is an older language, right? But it's a big deal, important language. It kind of set the standard for like all of those languages at the top, those top 6. And even the ones outside the top 6, like VB, PHP, SQL is entirely different. Assembly is entirely different. Go is going to be similar. They're all C-like. They were all basically clones of C, but they looked at C and they're like, well, C is great and all, but what if we did instead? So I think my guess of the order is going to be C is the oldest, then C++, then Python. Python came out in like '89, I think. Then Java. I don't know, C#, JavaScript, it's hard to say which one's the same. Now, to give you just a warning, Java and JavaScript are entirely different. Their syntax is similar in the same way that the syntax between Python and Java are similar. But Java and JavaScript, it's just, the joke is, Java is to JavaScript as ham is to hamsters. It's just, they're really not related at all. Just as an FYI. A lot of people assume Python's like new. No, it's old. It's been around for a while, right? But maybe I shouldn't call it old, but it's not as young as people would think it is. All right. Tuples, yeah. Starbucks, yeah. So tuples are fantastic. They're great. If you need a place to just store some data quickly, group it together, throw it in a tuple. You can throw it in a list too. Tuple might be a better choice. At the end of the day, it's really not going to matter so much. Now, these three things right here I'm going to be talking about, tuples, dictionaries, and sets, they're data structures. Like lists are data structures. They're data structures. But a list is a very general purpose data structure. It's commonly used. It's got a lot of bells and whistles that we like. It's very common. Tuples, dictionaries, and sets are not as general purpose. But what they're good for, they're good for. If you have a situation where you could use a dictionary, use the dictionary. If you have a situation where a tuple is going to do the trick, use the tuple. You can use a list, it's fine, but the advantage, the strengths, the purpose of that tool is to be good at what it's good at. A list is general purpose, right? It's like a jack of all trades, right? But whenever you have that special problem and you can use a special tool for it and it's really well designed for it, yeah, use it. And we'll see really good examples of this with sets. Now, dictionaries. So I talked about tuples, dictionaries. In some programming languages, they're called maps, key value pairs. Python, they call them dictionaries. These are, sadly, we won't really get an appreciation for how amazing they are in 161. They are, of all data structures we're going to talk about, they're the best, they're the coolest, they're fantastic. But they're not like as general purpose as a list is. But dictionaries are phenomenal. And I'll start by showing you, I think the best way to kind of see how this works is with an example. Here I'm starting with an empty dictionary. And I'm adding 3 values to the dictionary. Every value that I add to the dictionary has a key associated with it. A key needs to be unique. So here I'm adding, imagine this is like student grades. Maybe their first name isn't a good key because they might not be unique, but maybe something like their student email or student number would be better, but that's beside the point. We have a key, a unique key, and then we associate with that key a value. So here I'm adding 3 values. I'm taking the key Billy, and I'm assigning it the value 74. Now, the values don't need to be unique. The values don't matter. They can be whatever. The key's got to be unique, because if they're not, well, it'll be pretty obvious why that won't work in a moment. But Billy, 74, Sally, the key Sally has the value 88 associated with it, and the key Jimmy Bob has the value 99 associated with it. All right? And then I print out the dictionary, and there we go. And what's cool about this is this should look familiar-ish. If this was a list, it would be like saying something at some index in the square brackets is equal to some value. But what's neat about a dictionary is you can index the dictionary with a lot of different things. Anything that we call hashable. More on that briefly in a moment. So I have, it's almost like, okay, so I'm saying some dictionary at the index Sally equals 74. But of course with lists, you index lists with like list indices, right? It's an integer, like 0, 1, 2, 3, right? Where there's no 0, 1, 2, 3, it's Billy. And if I wanted to get a value from a list at some index, I would say some list at the index I want. So some list at index 7, and it gives me whatever's stored at index 7, assuming it exists. But here, no, I go Billy. And it tells me 74. So at this point, what you should observe is that, oh, it's like a list, but instead of indexing things with an integer, you index it with whatever you want, some key. Now you can't do anything as a key. For example, if I were to go down here and say, okay, equals an empty dictionary, and then QWE at, if I want to use a list as a key, 0, 1, 2, QWE at index of the list 0, 1, 2 equals 7, it's going to say no. Unhashable type list. And you might look at this and say, well, yeah, what would that even mean? That's kind of weird, right? Like you're indexing something with a list. I don't really see that. But you know what I could do? I could I can index it with a tuple. Tuples are hashable. So I actually could still do it with like a linear collection as a key, which is weird, but I can. But there are restrictions on what you can have as a key. The key needs to be hashable. And I'll talk about that in a moment. Very high level though. So yeah, now the reason the keys need to be unique is, well, what would happen if I were to say, like, oh no, I have another Billy, and their grade is 6. Well, all that, what's wrong here? My, some dictionary, yeah. It's not that it's not going to work, it goes back to this, it goes back to, like, the list at index of Billy is now changed. In the same way that if I go and modify some list at some index, it just modifies it. So I can't have 2 keys in there because, well, we have a conflict. There's only one index for Billy because they got to be unique. Any questions so far? Now, an example of where this might be really handy is, imagine I wanted to, for whatever reason, I decided I want to write a program to store my students' grades. And what I could do, if I'm not thinking about dictionaries, I'm just thinking about lists. What I could do is I could store each student record as a list, or a tuple, whatever. But I can store it as a list, where the first index of the list is the student name, and then the next index is going to be their grade. The list only needs to be length 2. I mean, I could have more if I want, like, more data. But yeah, I'll have each student be in a list of length 2 with their name and their grade. And then I'll store each of the students in a list. So I have a list of lists of student names and grades. Remember, it's a list of references to lists that contain, right? And to go back to like, let's get rid of that. That's a spoiler right there. You could think of like, okay, if I have, imagine like that's a list of a student name, name. Comma, grade. Right? Then, if I have a list of that, and I just make a list of these lists, and of course, all of this is wrapped in like a bigger list, you can think of it as like a table of data. Or going to what you were asking the other day, like it's kind of like a matrix, I guess, right? But it's a table. Now, really, it's a list of references to lists that contain information. But we can think of it like this, as it's often a little easier to think of it like this and reason about it this way. Is this clear? Now, if I had a list of lists of this, and there was like, I don't know, 100 students in here, and I said, okay, I want to know, assuming the list isn't sorted alphabetically or anything. Now remember, lists have an order, but that doesn't necessarily mean they're sorted. When I say order, I just mean that the thing at index 0 comes before the thing at index 1, which comes before the thing at index 2, etc. Right? So there is an orderness there. If I said, I want to know Sally's grade, how would I find it in this list? What algorithm have we been talking about a lot that we would need to go look for Sally's name? A linear search, right? You start at the top of the list and you go like, is this Sally? No. Is this Sally? No. Is this Sally? And you keep going until you find it or until you don't. Right? And again, I know I'm going to sound like a broken record. If there's 100 students in the course, worst case scenario, how many things do I have to look at to find Sally? What if it's 1,000? Right? If I double it, I double it. It's a linear time algorithm. And again, I know I said this before, but I'm going to say it again. There's a nuanced difference here. When I say linear, I don't mean the total amount of work the algorithm is doing, like the function is doing. What I mean is, how much does the amount of work the algorithm has to do change as the input size changes? So when I double the size of the input, I do double the amount of work. That's the idea there. So I'd have to do a linear search. And there's nothing wrong with that. But, yeah, so I'd have to do a linear search for Sally. It returns the record, and then the grade will be whatever the student record is at index 1, because remember, this linear search would have to be looking for my grades at index 0, because index 0 would be, each student's record at index 0 is the student's name. We return the whole student, we get the grade which is at index 1 in this hypothetical world. Alternatively, if this was stored in a dictionary instead, so not a list of lists that contain student names and grades, if I stored it as a dictionary where each key was a student name, there's no linear search anymore. We just immediately go look up Sally and it tells me, oh, it's great, which is pretty great. Now, so obviously this syntax is nicer. It seemingly gets rid of the need for a linear search. But I know, if you've been paying attention in this course so far, we just finished talking about sum yesterday, or 2 days ago, whenever the class was last. And I said, oh, Python has a built-in function called sum. And if you give it a list, it'll sum up the contents of that list. But I told you to write your own sum function. And you had to go iterate, you had to write a loop to look at each thing in the list and add it to some running total and return the value. And obviously that would be linear time, right? If I double the amount of numbers I need to add up, I double the amount of work I need to do, right? And then if you were to think, well, okay, let's look at Python's, oh, it's a linear time algorithm, but the other one I could just call sum and it's going to do it for me. But if you go and crack open the hood of Python's built-in function sum, it's going to look a hell of a lot like exactly what you wrote. Meaning, although you didn't write the linear search, Python was still doing it. Oh, I guess not linear search there because this was sum. Although you didn't write the loop over each thing to add it together, you'll open up the hood of Python sum, you're going to see basically the same code. So your naive assumption would be like, obviously it's better to use the Python's built-in one because it's faster. It didn't need to have a loop. But it did inside of it. As soon as you look inside, you go, there's the loop. It just hid it from you. So you might be thinking the same thing here with dictionaries. Okay, great. When you used a dictionary, you didn't have to write the linear search. But I'm guessing if I open up the hood on the dictionary, I'm going to see that linear search. And if you're thinking that, you're wrong. No, it doesn't need to do it. With the dictionary, and there's going to be several asterisks associated with what I'm about to tell you that I'm not going to get into. With the dictionary, if you gave me a dictionary of 100 students and you said find Sally, it would take me 1 unit of work. If you doubled it, it still takes 1 unit of work. If you multiplied it by 1,000,000, I still only have to do 1 unit of work. The amount of work the dictionary needs to do is what we say constant time. I don't care how big your input is. It takes the same amount of work for me no matter how big it is. There's a couple of asterisks there. Which is wild. If you have an algorithm, if you're sitting there and I tell you, okay, this is a really important job, I need everyone to write code to do X, Y, Z. And you write the code and your algorithm is linear time, that's good. But the person sitting next to you is constant time. Your solution, your linear time solution, is abysmal and you should feel terrible about yourself. Because if you can have a constant time solution for the same problem as someone else has a linear time one, the constant time one is undeniably better. It's going to run faster, it's going to use less resources, people don't need to wait, it uses less electricity. There's a lot of reasons we want the constant time algorithm. This all now leaves you wondering, okay, how the hell does it work though? It just magically is constant time lookup? How the hell does it do it? Now, there are asterisks associated with it, and I am not going to go into the full details here. I'm going to explain it to you at a very high level so you're aware of it, so you can learn a little bit about it. But this dictionary's outside the scope of this course in terms of how hashing works and everything I'm about to show you. Knowing about dictionaries is part of this course, but knowing how they work under the hood, we're not going to worry about that in this course, or even next semester. But I'm still going to show you. And it all comes down to this magic thing we like to call a hash function. H of x. All right? We've got memory. And bear with me as I just try to draw some blocks here. Right? We pretend it goes on forever. Right? So this goes on forever, but for whatever reason, I've kind of zoomed in on a couple of sections of RAM just because. If I had a list, we already saw kind of how Python's going to store the list in RAM. Or your computer's going to store the list in RAM. It's going to find a nice contiguous chunk of memory. If I have 10 things that I got to put in there, we know, okay, we could put the 10 things nicely in the spot of 10 units of RAM and everything fits nice and tight, good, we're good to go, right? That's how the list is going to work. And then if you want to do a linear search, your computer just iterates over those memory addresses effectively and goes like, okay, oh, there's the one I want. With a dictionary, what the computer does is it says, okay, here is a gigantic chunk of RAM. A really large chunk of RAM. And you're going to give me a key that has to be hashable. Meaning, I give it a value that I can throw into this function. And when I say H of Sally, this hash function turns the key into a unique memory address. It turns it into, for whatever reason, when the key Sally got thrown at this hash function, it went to this memory address. It turned it into some arbitrary memory address. It's deterministic, meaning every time I give it Sally, it gives me the same number. But this function, this magic hash function, I give it a key, it turns that key into a unique memory address. So then later, if you say, well, what did I put at Sally? You just go, okay, here, hash function takes Sally, where do I look it up? It's kind of like a lookup reference guide, right? If I want to assign a value, I say, okay, dictionary at Sally, it goes, oh, that's this memory address. Put in the number 88, or 70, what was it, 74, 88? 70, 88. Sally's doing well. 88. Right? So dictionary at index Sally, at key Sally is 88. And then later you go, what was there? You go, okay, hash function. Where do I look for Sally? And it goes, oh, at that memory address. And you go, you just look it up. Then, for the sake of space, let's just then we've got H of Billy. And that'll get hashed to, I don't know, this memory address down here. And then we did the same for Jimmy Bob, and it goes to another one. So it ends up being this lookup table. You just throw it in a hash function. The hash function is constant time. It just magically converts a string into a unique memory address. It's deterministic. Every time I give it the same string, it gives me the exact same memory address. And there we go. The downside of this is it takes up a lot of, there's going to be a lot of wasted space. And imagine for a second, I create a dictionary, and the computer says, okay, for this dictionary, let's set aside 500 chunks of RAM for this dictionary. But if I start adding more and more and more things to the dictionary, I'm going to run out of spots, right? And I might even run into what we call a collision, a hash collision, where what happens if that key, when it goes through the hash function, gets converted to a memory address that some other key gets converted to, which is inevitable to happen. The number of things that can be hashed is literally infinite. But the number of things that can hash to is finite. Meaning collisions are inevitable. So this is where all those asterisks pop up in terms of like the lookup speed, how constant time. There's some stuff that might need to happen behind the scenes. But in general, that's how it works. That's how it just magically does it. But by doing so, we need this magic hash function. And we need a lot of RAM. But it's the trade-off. Uses a lot of RAM, but I can find the solution in constant time. Maybe that's a good thing. Or maybe you really don't have a lot of RAM and the linear search isn't that big of a deal. Okay, then go with the list and do a linear search. There's always trade-offs. It's always about picking the right tool for the job. Dictionaries are often your go-to trick for making your algorithms a lot more computationally efficient. Any questions about dictionaries hashing or anything?
What's the best way to work around the issues of the
So you don't need to deal with it. The dictionaries does it all by itself behind the scenes. Now, in 255, so not next course, but the course after, you'll actually do a deep dive into hashing and how to deal with all these different situations. So as if you can make your own dictionary. But we're not going to touch that right now. That's well outside the scope of this course. Other questions? That was a good one. All right. And sets. Who here has ever heard the word set before? Who here has taken like discrete math and you're all familiar with sets? One person. 2 people, 2.5, 3 people. So a set. A set, it's just a collection of information, but sets don't really have an orderedness to it. Python will kind of preserve an ordering. If you create a set and have things in an order, it'll kind of preserve it, but by definition there's no ordering to elements in a set. They just exist. And what's neat about sets is all the values are unique. If you try to add a value to a set that already exists, it just kind of ignores it, right? Because sets are just unique values. They have to be by definition. So if I made a set of these students that are in Computer Science 161, this is how I would do it. Make a set of that. Great. Greg, Anna, Sally, Frank, and Frank. But when I print out the set, Python just ignores the fact that there were 2 Franks. It really doesn't matter. Let's see. I'm curious what the order will actually come out as, if it'll be the same. Greg, Frank, see, look, they didn't even show up in the order I added them. The order really doesn't matter with sets. And if you say, but why? Like, because whoever said this is what a set is, said so, and then we went with it. All right? So that's the idea of a set. If you say to me, well, what if I want two things in it? Then I say, then don't use a set. Use a list. All right? A set is designed for what it's designed for. It's a tool for a job. I could then do I made another set for Math 106. Who here's taken 161? Okay, obviously. And Math 106 right now. A couple people, right? So you would be in the Math 106 set and the Math, or the CS 161 set. Okay? You can add things to a set too. I'm just showing you here. There we go. Now what's neat about sets is obviously it keeps the uniqueness here. Each element has to be unique. But what's neat is I can say something like, well, print and this will tell me who's in both. But because it's sets, it eliminates any duplicates, right? There's only one Frank in the last one here, but Frank is taking both 161 and Math 106. So it allows you to say, tell me who's in both. And that's great, that's fantastic. And when we think about union, for example, it's kind of like an OR. It's kind of like the logical operator OR. They could be in both. They might both be true. They might both, a student might be in both courses, but I don't care if they're in both. I just care about, are they in one or the other? That's what the set's giving you back. It's kind of like, the union is kind of like an OR. And similarly, there's something called the intersect. This is more like the AND. Tell me who's taking 161 and 106. And it'll return a set of those that are in both. So instead of the union, I can ask the intersect. Or if did I spell it wrong? No. Maybe intersection, yeah. There. So there's only two students in both courses that are taking both courses. Only Sally and Frank are in both, which is great. And if you're thinking to yourself, okay, this is really cool, but I'm not seeing I'm going to use this very often, right? Like I can see its value, but when am I really going to use it? My answer is when you want to do stuff like this, and you say, how often am I going to do that? And I'm going to say, I don't know, it's up to you. But when you want to do it, you should use the right tool for the job. A set is really not a general purpose. It's general purpose in the sense that you can load it up and use it whenever you want. But in terms of its utility, you're not going to use it in place of a list. A list is far more generally applicable. But in a situation where you want to ask questions like this of your data, you're going to have to do a lot of work if you use a list. If you use a set, it's one line of code. Tell me the intersect. You can even do the difference. Now what's cool about difference is it's actually the order matters. It tells you who's in one but not the other. So if I ask the question, who's taking 161 but not taking Math 106? Well, that's Greg and Anna. Because Sally and Frank are in both. But if I switch the order, if I say Math 106 difference with CSCI 161, it gives you different results. It's the order matters. Yeah.
So set would be like a built-in function?
Well, it's a built-in data structure in the same way that it's like a built-in list. There's lists. Yeah. So they're built in. And what do we call, like right here, I said Math 106. What is Math 106? It's not a trick question. It's a set, right? It's a reference to a set, fine, but it's a set. In the same way that it's not really a list, it'd be a reference to a list, but it's a set. And if I take something that's a set and I say dot difference, and I'm calling it like a function, what do we call these things again? Methods, that's right. It's like a function, but it operates on the instance of the set that I'm calling it on. It's the implicit argument. So if I were to give you a problem and I asked you something like, if I gave you a list, if I gave you a book, or let's say you've got your favorite book and somehow you're able to load it up into Python and save it as a string. You can do that. It's going to be a big ass string, but you can do it. And you can throw that string into a set. And I ask you a question, how many unique words are there in that book? You throw it into a set and you say, all right, how big is the set? And it'll tell you how many unique words are in there. Because anytime there's probably a lot of thes in your favorite book, right? But the will only exist once, right? So you only need to count it once. Great. If I give you another book, you load it into a set. I can now ask you ask questions like, what words exist? How many unique words are there between the two books? You do the union and get the length. Does anyone know what we call like the size of a set? There's a special word we use. Because sets aren't really, like a list has a length because a list is like very linear. Right? There's like a start and an end. But sets don't really have a length, right? Because they're not really linear, they're just kind of like this like blob of data. So asking the length of like this blob is kind of a weird question. So we use a different word. Does no one know what we call, how the bigness of a set? I'm certain someone in here has heard the word before. It's called, come on, it's the cardinality. The cardinality. Raise your hand if you're like, yeah, okay, I heard that before, yeah. Cardinality, well, whatever, fine, it's the cardinality. That's what we call it. So you take the cardinality of the set, which in Python you still ask it the length. It knows, but mathematically speaking, we would use the word cardinality. If I want to know how many unique words are there, how many words exist in that book that aren't in that book, and vice versa, how many words are there that are in both books, all of these types of questions, which you might say are kind of like funny questions that you might ask, why would I ever want to do this? Yeah, in reality, I think I've used a set maybe less than 10 times in my life, right? But when I needed them, and they did the trick. All right, cool. I'll see y'all later.